All right, so in today's video, what we're going to look at is the vapor compression refrigeration cycle. Primarily because I'm going to stumble over saying that, I'm simply going to refer to it here on out as the refrigeration cycle. But I want you to be aware that there are more than just the vapor compression refrigeration cycles out there, namely the Rankine refrigeration cycle. Now, the reason we're choosing this cycle to look at as opposed to the Rankine refrigeration cycle is primarily to do with the amount of times that you're going to see the vapor compression refrigeration cycle in industry versus the Rankine refrigeration cycle. Many of you may never ever come across the Rankine refrigeration cycle, but almost all of you will encounter the vapor compression refrigeration cycle. And so it's a very good cycle to learn. It's a very good cycle to understand and to work through not only understanding the thermodynamics, but understanding the logic on how we're about to build this ideal system. And so I want to talk a little bit, before we get too deep into the weeds here on the cycle, I do want to talk about building this ideal system, which is what we're going to walk away from these first two videos with, really a set of assumptions that we've really made to make this best case scenario cycle. And you might be wondering, well, what's the purpose of this? Why are we doing this? Is it just so we can do some sort of academic calculations? Does it have any sort of bearing in industry? And the answer to that is yes, it does. It has a lot of bearing. But also the reason or the logic behind those assumptions, how are we building those assumptions is very important. And you need to be well versed as a chemical engineer in building these types of assumptions to assess at a high level these different types of systems, whether they're going to work economically, whether they're going to work practically. And so as we work through this, I want you to pick up both the assumptions that we're building on the system that we're going to have here on the board, but also the methodology behind how we're going about this is also very important. So with that said, let's get into it. So let's break up this refrigeration system into its four major components. And the four major components of this refrigeration system are, and you can do these in any order because, as you'll see, the cycle is circular, so who's to say where we start at? So we got to pick a starting point, and I've picked the expansion valve. So the first major piece of equipment here is the expansion valve. And again, just because for ease of writing here, I'm just going to shorthand this as EV for expansion valve. The second major piece of equipment is the evaporator. And I'm going to label this shorthand Q, uppercase Q, lowercase c, give you a little bit of understanding of why I'm doing it this way. The expansion valve EV probably makes a little bit more common sense. But the Q, as you'll learn if you haven't learned already, is a common symbol for heat transfer. This evaporator is a heat exchanger. The C here is denoting that this is the heat exchanger on the cold side of this system or this cycle. This cycle is actually a cycle that has a cold side and a hot side. We'll learn a little bit more about that as we go to breaking down the system. The third major component of this system or of this cycle is the compressor. And I'm going to shorthand this WC. The W is just really kind of shorthand. Up to this point, you should have seen this, hopefully, in your thermodynamics course, where we kind of shorthand work as W. So we're looking at the work because the compressor is putting work in the system. And the C there is not for the cold side, it's for the compressor. You can come up with any shorthand you want. I'm just going to show you the one that I'm going to use throughout the videos. The fourth major component of this cycle is the condenser. And the condenser, like the evaporator, is a heat exchanger. So I'll use Q as part of its abbreviation and H as the other part, because the condenser is the exchanger on the hot side of this cycle. Now, what we're going to do, we've kind of listed out the 4 major components, and we're going to assemble those components here in something called a PFD for shorthand, or process flow diagram. It's really just going to be a big picture schematic to help us understand how these 4 major components are linked together, and how can we visualize them working together to bring about what the cycle is ultimately supposed to achieve. But before we get to drawing out that PFD, I want to talk a little bit about what the refrigeration cycle is actually achieving. And for many of you, you've had an AC unit, or you've had some sort of refrigeration that you're aware of, and you know that a refrigerator makes things cold, or it gets your food cold in the refrigerator. But I want you to think a little bit more along the lines of thermodynamics. Will that refrigerator get cold just naturally? Will your house get cold naturally? Let me ask it maybe in a better question. Let's say it's really hot outside one day, and you've got your AC running. If you were to turn your AC off, would you expect your house to continue to get colder? Or would it start getting hotter? Well, the answer is it would start getting hotter, right? That is because heat naturally is going to flow from a higher temperature medium to a lower temperature medium. And you might be laughing at this line of questioning as I'm going through it, but it begs the question, how is your AC able to take energy from a cold system and dispel it to the hot system outside? Because naturally, if we turn the AC off, that wouldn't happen. And that's fundamentally what you need to understand about this cycle. How is this cycle able to achieve that goal? How is it able to take energy from a colder temperature system and dispel that energy to a higher temperature system? Something in the natural world that we wouldn't see happening unless we put work into the system. That's the missing component there, right? If we were to turn the AC off, there would be no work being done to the system. There would be no work being done to your house. And so what's going to happen? Natural thermodynamic, the thermodynamics is going to state that the hotter medium is going to now give up its energy to the colder medium, and they're going to eventually reach thermal equilibrium. So with that little thought experiment there, we've deduced now that this compressor, or maybe potentially something, is doing work with this cycle that's overcoming some of the quote-unquote laws of thermodynamics, right? We're not really overcoming those laws. The compressor is, if you want to think about it this way, is paying an entropy tax. You're having, in order to achieve this thing that goes against what we might call the laws of nature, we have to expel energy. We have to fight against entropy, so to speak. So just an important thought experiment as we go through this. I want you to understand, I'm always going to bring you back to understanding fundamentally what's going on in this system. That's your takeaway from this. If you don't understand what's going on in these systems, if you don't understand first principles, then you can do all the calculations that you want to. You can solve all the home problems that you want to. But the amount of value that you're going to add to your team and industry once you get out into the real world will be minimal, because you don't know how to think through the problems. You don't know how these things actually work. Okay? So let's look at this system. And again, the system is circular, so we can really start with any point. But I'm just going to start as we listed them here. So I'm going to start with the expansion valve. And again, we're going to draw what in industry you would call this sort of a process flow diagram, or PFD. So if we start here with our expansion valve, and coming out of our expansion valve, the working process fluid will then travel to our evaporator, QC. Let me put my abbreviations here on the expansion valve. Now, as the working fluid travels out of the expansion valve to the evaporator, we're going to term this state right here state 1. We could call it state A, we could call it state 25. Doesn't matter. Again, we just want to label this to say, okay, when we say state 1, we're talking about the working fluid in between the expansion valve and the evaporator. So if your teacher labels this as something different, he or she is not wrong. So the next step in this sequence is after we come from the evaporator, the working fluid, the refrigerant, is going to come out of the evaporator and go into the compressor. Now between the evaporator and the compressor, we will call this state 2. The next step in the sequence is after the compressor, the fluid is compressed, discharged, and then makes its way into the condenser. Again, another exchanger. Between the compressor, after the fluid, the working fluid or the refrigerant is compressed, going into the condenser, we're going to call this state 3. Now, our condenser, the last step in our loop here, we're going to connect our loop. So the fluid, the working fluid, is going to come out of the condenser and go back to the expansion valve to go round and round. This state here between the condenser and the expansion valve, we're going to call state 4. All right, we haven't talked about what's happening here. We've just talked about the working fluid. We've talked about the sequence in which these major components are assembled. So you're kind of left again here with just a high-level diagram. We don't even know what's happening to the fluid in any one of these cases. So we're going to add that layer right now. So here in state 1, let's look at across the expansion valve between state 4 and state 1. Now I've called these states because it's ultimately what we're going to look at them as. So remember, a state has pressure, temperature, entropy, enthalpy, all these different state functions. So here, site 1 has pressure 1, it has temperature 1, we'll call, it has entropy, excuse me, I wrote entropy 2 there, entropy 1, and enthalpy 1. And these are all referring to the state functions or the states at state 1. So what's this fluid here? How do we identify it? It's got a pressure, it's got a temperature, it's got an entropy, and it's got an enthalpy. Same thing with all these, but I'll go ahead and write out because we're going to evaluate between 4 and 1 what's happening to the fluid as it comes across the valve. So what happens here is, as it comes across this valve, what we have on step 4 over here is a higher pressure system, ultimately generated by this compressor. So the pressure over here at state 4 is higher than the pressure here at state 1. So we might write P4 is greater than P1. Now we can go through and further deduce some other things by making some assumptions. And so these will be our first kind of round of assumptions here. We're going to assume here that this at state 4, and this will make more sense once we come back around, but we're going to assume, for a starting point, state 4 is actually saturated liquid. Remember, saturated liquid is a liquid that is still in vapor-liquid equilibrium. It's not a subcooled liquid, but it's a liquid that's just hit the point of equilibrium. So it's got effectively one molecule of vapor that's flashed into the vapor space, but it's at its saturation point. Now, as the fluid comes from state 4 to state 1, what happens is this control valve actually acts as a restriction, meaning that just restating what we've already stated, meaning that the pressure here is going to be greater than the pressure here. And what winds up happening is because now we have a reduction in pressure, we also, because we're at, the liquid was already saturated, so we know that we're have vaporized some things here because, I'll give you that logic here, the pressure has gone down. So because we're at equilibrium, and we know that we're working, or we've assumed here, that we're working with a pure working fluid, a pure refrigerant, that constrains all the other state functions. So if the pressure goes down, the temperature also has to go down. And that's effectively what's happening as we come across this valve. We see a drastic drop in pressure depending upon how you size your system. So this pressure drop may be bigger in certain units and smaller in the other ones. It's going to be, again, dependent upon your design. But what winds up happening is now as we drop that pressure, we wind up getting a mixed system. So over here at state 1, we have vapor and we have liquid. And how much of each, again, is going to be dictated by how you designed your system, how it's operating. So now let's look at going from state 1 to state 2. What's happening here? Well, what's happening here is, as we come from state 1 to state 2, we go through this exchanger here, the evaporator. And ideally, if you designed your evaporator and your system correctly, what you would want to wind up with is saturated vapor here at state 2. So effectively what we're doing is we're sending this vapor plus liquid system. We don't know how much vapor or liquid at this point, but we could calculate that if we constrain the system some more. But we would want to design the system such that as we went through this exchanger, it sucked or it picked up enough heat from the surroundings in this exchanger to evaporate all this liquid. Again, we're looking at latent heat here. And again, so we're going to evaporate all this liquid. Everything now is going to be saturated vapor. Just like saturated liquid, this is still vapor-liquid equilibrium. And so we're still constrained here under vapor-liquid equilibrium. We'll also have a state here of pressure 2, temperature 2, entropy 2, and enthalpy 2. Again, all we've done here in this evaporator is basically pick up heat. Now, from going from state 2 to state 3, so if we go ahead and just write out all of our state functions we've been looking at. Now what happens is as we go from state 2 to state 3, we have this compressor. And all the compressor is doing is imparting work to this saturated vapor. So it's imparting work, increasing the pressure, and likely increasing some of the temperature, and what we wind up with is something we would call superheated vapor, which is really just a fancy way of saying it's vapor that's no longer in equilibrium with its liquid phase anymore. So it's not saturated, it's superheated. So we've increased the pressure, which means that one of the deductions from here is that because we've put work into the system, we've increased the pressure, we can know that P3 is going to be greater than P2. Now the last step here in our system is going from step 3 to step 4. And what we want to do ultimately is design this heat exchanger. Remember, I just kind of assumed here we're going to have saturated liquid, and we're getting back to how does this become saturated liquid. We would ultimately design this exchanger to take this vapor from superheated vapor to saturated vapor at the higher pressure and ultimately continue to cool it through that latent heat regime to saturated liquid. So again, this is just taking out heat or cooling it in this instance. So over here, if we were to divide our cycle in half, what we have over here is our cold side. Why do we call this our cold side? It's because the temperature of our working fluid over here is colder than the environment in which it's removing heat from. We call this the hot side because the working fluid here is hotter than the temperature in which it's expelling to. If you haven't got to this in thermodynamics, one of the major proponents of heat transfer is temperature difference. But heat is going to travel from a higher temperature to a lower temperature. That's why it's important over here, if this were your house and you want it to be at 74 degrees Fahrenheit, the temperature of your working fluid in the system has got to be 74 at best case, but it's more than likely you're going to have to be lower than that to achieve proper heat transfer. You'll get into that in a later class. But the point being is, at a minimum, this temperature over here on this cold side has got to be 74. It can't be hotter than that. On the hot side, if we're going to dispel that heat we just sucked from over here out to the environment, so we would need to know what the environment temperature is. In Louisiana, which is where we're filming these videos, I mean, it can run up to 105 degrees Fahrenheit some days. So your working fluid is going to need to be at least as hot as 105, but ideally it needs to be hotter than this. So the work that you're inputting from the compressor needs to bring this temperature of the condensing fluid up to 105 or greater for this cycle to work. So I hope we're at the conclusion of this first video. Just some takeaways. Remember, what did we look at? We really just built the basic structure for our refrigeration system. We looked at the 4 major components. Okay? Then we assembled those components within the refrigeration cycle itself to see how they work, and really kind of what's happening to the working fluid. How is it achieving what it's achieving? And how is it assembled in a certain way to achieve that desired result? And we also looked just at some deductions here from, okay, if this is working, if this is how this works, then we can infer that the pressure at 0.4 is higher than 0.1. We didn't assign a value to it quantitatively, but we can infer these things just from how the system should work. Similarly here, because we have a compressor compressing the gas, we know that P3 has to be higher than P2. How much? Again, that's going to be really based upon the design that you're looking at. But with that being said, we'll stop here for this video, and when we come back, what we're going to look at is how do we take this system that we looked at and build that ideal system, that benchmark, that perfect standard in which we can go out and evaluate maybe different cases with. Thank you.